Today in this session, I will talk on pH. I will explain how the water molecule undergoes reversible dissociation and the proton thus produced gets solvated. I will try to explain the pH scale and why it ranges from 0 to 14. I will also explain the relationship between pH and pOH. I will also talk about the difference between concentration and activity of ions in a solution and the dependence of pH on temperature of the solution. I will provide informations regarding the pH of different fluids that we encounter in our day-to-day life. Finally, I will talk regarding the effect of pH in the biological world as well as the effect of pH on important biomolecules like DNA, RNA, and protein. pH denotes acidity or alkalinity of a solution. It is defined as the negative log of molar concentration of hydrogen ions. For biological system in aqueous solution, this definition may be refined as follows. The protons in aqueous solution never remains free. It gets solvated by undissociated water molecules to form H3O+, the hydronium ions or higher oxonium ions. And the term concentration may be replaced by activity. In the later part of this presentation, we will explain the difference between concentration and activity. For better understanding of pH, it is essential to consider the dissociation of water molecules. The proton produced upon dissociation of water molecules remains solvated to form hydronium ion H3O+ and further solvated to form higher oxonium ions. The dissociation of water molecules may be reversibly expressed as H2O reversibly dissociates to form H+ and OH- ions. The velocity of forward reaction Vf may be expressed as Kf times concentration of undissociated water molecules. Similarly, the rate of reverse reaction Vr may be written as Kr times concentration of H+ times concentration of OH-. Equilibrium is defined as a condition when the rate of forward reaction and backward reaction is equal, and at this condition the relative concentrations of the reactants and the products remains the same. So at equilibrium, Vf equal to Vr or Kf times concentration of undissociated water molecules equal to Kr times H+ times OH-. Now at equilibrium concentration, Keq prime is defined as the ratio of the two rate constants Kf by Kr. So Kf by Kr equal to H+ times OH- divided by undissociated H2O, or in other words, Keq times undissociated H2O concentration equal to H+ times OH- concentration. Now, the values of Keq prime has been carefully estimated by electrical conductivity measurements, and the value has been obtained to be 1.8 times 10 to the power minus 16 at 25 degrees Celsius. And as we know, the molarity of water is 1000 divided by 18 equal to 55.5. The value of H+ times OH- comes to be 1.8 times 10 to the power minus 16 multiplied by 55.5 equal to 1 times 10 to the power of minus 14. So, the ion product of water, that is Kw, which is once again expressed as H+ concentration multiplied by OH- concentration, is 1 times 10 to the power of minus 14. As we know, that upon dissociation, one water molecule produces one proton and one OH minus ions. For pure water, when no acid or alkali is added from outside, the concentration of H plus equals the concentration of OH minus, and both equals 10 to the power of minus 7. And since pH is defined as the negative log of hydrogen ion concentration, pH of pure water when no acid or alkali is added from outside turns out to be minus log 10 to the power of minus 7 or 7. So the neutral pH is said to be 7, and any pH below 7 is acidic, or in other words, pH 0 to 7 is acidic and pH 7 to 14 is alkaline. pH and pOH. pOH is similarly defined as the negative log of OH minus ion concentration. For aqueous solutions, pH plus pOH always equals 14. It is true even when external acid or alkali is added to it. This table shows the relationship between pH and pOH. When the hydrogen ion concentration is 1 molar, pH is 0 and pOH is 14. When the hydrogen ion concentration is 10 to the power of minus 4 molar, the pH is 4 and the OH minus ion concentration becomes 10 to the power minus 10 molar and pOH is 10. So pH plus pOH is always 14 irrespective of the solution is neutral or acidic or alkaline. This table shows the pH of different fluids that we get exposed in our day-to-day life or we know. For example, the battery acids and other strong acids have a pH of 0. The hydrochloric acid or the acid secreted in our stomach has a pH of 1. Lemon juice, grapefruit juice, tomato juice have pH at the acidic range ranging from 2 to 4. pH of saliva, urine and many other body fluid is slightly acidic at pH 6. Pure water has pH 7. Seawater is alkaline and the pH is 8. Then baking soda, ammonium sulfate, soapy water has alkaline pH of 10 to 12. And finally, the oven cleaner and the liquid drain bleach has the highest of pH at 13 or 14. What's the difference between pH and P hydrogen ion concentration? As we discussed in our first slide, pH means the negative log of hydronium ion activity and P hydrogen ion concentration means the negative log of hydrogen ion concentration. So the discrepancy is between activity and concentration. Activity is defined as concentration times the activity coefficient. For dilute solutions, there is not much of difference between activity and concentration. As a thumb rule, pH is P hydrogen ion concentration plus 0.04. The analogy is like that, suppose in a factory there are 100 workers, but it is not expected that at any point of time all the 100 workers are working. The ionic strength of any solution also depends on the presence of other ions in the media. A good example is that the pH of 0.05 molar potassium hydrogen phthalate solution can vary its pH to as much as 0.5 unit as a function of added potassium chloride concentration, although potassium chloride by itself is neither acidic nor alkaline, it's a neutral salt. There are instruments for measurement of pH. pH paper is a very handy and easy to use device to monitor pH. However, it gives only a gross measurement of pH. It is used in laboratory for day-to-day monitoring of pH of microbiological broth. All you need is to add 1 drop of the solution onto that paper, and the paper changes its color instantly. You match the color with a given color range and you get the pH. Portable pH meter like pH pen type of devices are also very handy, portable, and they give you accurate measurement of pH. However, the most precise instrument to monitor pH is a pH meter, which is used all over the world for accurate measurement of pH. Now, is pH dependent on temperature? The answer is yes, because dissociation constant of water is at the heart of pH, and dissociation constant of water is dependent on temperature. The table shows the relationship of temperature with the Kw, or the ion product of water. For example, at 25 degrees Celsius, the ion product of water is 1 times 10 to the power of minus 14 and the pH value comes to 7. But if the temperature of the solution is 10 degree, the value of Kw is 0.293 times 10 to the power of minus 14 and the pH is 7.27. And if the temperature of the solution is 50 degree, then the Kw goes to 5 times 10 to the power of minus 14 and the pH is 6.63. So, 6.63 is the neutral pH at 50 degrees Celsius. Anything below 6.63 at 50 degrees Celsius is considered acidic, and any pH above 6.63 at 50 degrees Celsius is considered alkaline. So, it is important to mention the temperature of the solution while expressing its pH, and it has to be noted that 7 is considered as a neutral pH when only at 25 degrees Celsius. Now, pH profoundly affects the biological world. Bacterial growth depends on pH of the medium. Accordingly, bacteria can be classified according to their growth pH. Acidophiles are bacteria that thrive in highly acidic conditions, usually between pH 1 to pH 5.9. Acidobacterium, Thiobacillus acidophilus, Acetobacteria are examples of such acidophiles. There are bacteria that grow and thrive between pH 6 to pH 9, and they are called the neutral philes. Most of the pathogenic bacteria that cause disease to human beings belong to this category. There are other bacteria which are called the alkaliphiles. They thrive at alkaline environment with a pH of 9 to 11 in the natural carbonate rich soils or at the playa lakes. Bacillus okhensis is one such example. pH affects activity of proteins and enzymes. As is shown in this graph, all enzymes have an optimum pH at which their biological activity is maximum, and activity declines above and below that pH. Proteins and enzymes have different pH maximum values. For example, in this diagram, pepsin has a pH optima at around pH 2, which is highly acidic. Urease has its pH optimum at around neutral pH of 7, whereas glycine oxidase has a pH optima at around 9. The response to pH change of different proteins also varies. For example, glycine oxidase activity sharply declines below and above the optimum pH. pH affects nucleic acids. At low pH, deglycosylation of DNA takes place. The glycosidic bond between pentose and the nitrogenous bases are susceptible to cleavage at low pH. the bond between C1 of pentose and N1 of pyrimidine or N9 of purine is susceptible to low pH, and apurinic sites are created in DNA at low pH. At high pH, DNA undergoes denaturation. The two strands of DNA are held together by hydrogen bonds, and at high pH, the bases change their ionization property and they do not support the hydrogen bond anymore. So the two strands of DNA are spread apart, called the denaturation. Now I present a good example of pH controlling the color of nature. The flower of hydrangea occurs in nature with a color of pink to purple to deep blue, and it has been proved by scientists that the color of hydrangea changes depending on the pH dependent mobilization and uptake of soil aluminum by the plant. At lower pH of 5.2 to 5.5, the color of the flower of hydrangea is pink, and as the pH increases, the flower color changes from pink to purple and ultimately to blue at pH 6 to 6.2. We come to the concluding section of our session, and here are a few key points to remember. pH is the negative log of hydronium ion activity. pH 7 is said to be the neutral pH at 25 degrees Celsius. pH 0 to 7 is considered acidic, and pH 7 to 14 is considered alkaline. The ion product of water, that is Kw, is 10 to the power of minus 14 at 25 degrees Celsius, and this is the basis why the pH scale is between 0 to 14. Point number 3, for pure water at 25 degrees Celsius, when no acid or alkali is added to it, the hydrogen ion concentration equals the OH minus ion concentration equals 10 to the power minus 7 molar. pH plus pOH always equals 14 even when acids or alkalis are added from outside. And pH can be measured by instruments like pH meter, pH paper, and so on. pH profoundly affects the biological system. And lastly, the effect of pH on biological macromolecules. At low acidic pH, nucleic acids are deglycosylated. At high pH, DNA is denatured and RNA is degraded. All proteins and enzymes have an optimum pH for their function. The three-dimensional structure of the protein, which is essential for their biological function, gets altered at alteration of pH, and the protein loses activity.